Okay, so important to note here is for a steady creeping flow, the entire left side of this equation D is going to be set equal to 0. And then psi is going to become the E4 side term equal to 0. So looking at the spherical V phi, we're going to be able to write out the E4 side term as partial over partial r squared. Okay, so we have this in terms of partial r and partial theta. We're now going to be writing out the VR and V theta terms just from above. So we have VR and then we have V theta is equal to 1 over sine theta theta phi over d theta dr equal to 0. Okay, so psi for the third equation is going to be equal to negative 1/2 v infinity r squared sine squared. The first two parameters for this are just the boundary conditions to describe a no-slip condition. And the third, the psi, is describing the condition at the surface of the sphere. So if we assume that VR, v infinity equals cosine, and that v theta equals v infinity sine theta, we can postulate what equation we might need to find the like the equation for the flow around the sphere. We're going to call that FR. It doesn't really matter, it's just an equation. Okay, so we have that psi is equal to this FR sine squared, and now I'm setting the E equation. I'm plugging in this new FR sine squared theta where phi was above in the equation. So right at the end of this squared, we have FR sine squared theta. And we're going to want to simplify this. So the first step is we're going to be multiplying in that FR sine squared theta to both terms. So the first term, I'm putting sine squared theta in front over dr squared. And I'm adding, just repeating, sine of theta over r squared, d over, wait, get rid of that, d over d theta times 1 over sine, 1 over sine times d theta. And then we're going to need to make sure that you put sine squared at the end because we want to take the derivative with respect to theta of the sine squared. So the derivative is going to be 2 cosine sine, and then we see that that sine theta is going to cancel out with the above sine theta. We're then going to take derivative of 2 cosine theta with respect to theta again, and we're going to get negative 2 sine theta. Okay, simplifying the top equation. Here, let me, new page. So if we simplify that with the top equation, we're going to get, just rewrite it here, e to the 4th of psi equals to sine squared theta partial r fr plus fr sine squared theta times negative 2 over r squared. Okay, so now we are going to factor out the sine, and we're going to divide it over to the 0 side, and that's going to, we're going to be able to, we're factoring out that sine squared theta from the equation, and then we're dividing it over because we don't want this equation to be in terms of theta. And then we want the FR to remain outside, although we're not dividing that over. Our final answer is going to look like that. Okay, so the next step is we just found what we call the equidimensional equation, meaning we need to trial test this in solutions of the form of CR to the n. Okay, so in order to find the n values of this equidimensional equation, we're going to be plugging in CRn to the equidimensional equation to find possible values of n. Okay, so the above equation, I'm going to separate it out. It's squared, but it's easier if you multiply it together like this because we're going to be breaking it down and substituting CRn to each half individually. So CRn equal to 0. Next, we are going to be substituting in the CRn. So the right side of this is going to become n times n minus 1 times CR to the n minus 2 due to the r squared minus 2CR to the n minus 2. And the reason that these powers are to the n minus 2 is because n minus 2 is corresponding to the r squared that are in those terms. We're then going to simplify, and we're also going to expand the CRn to the other half of the equation, which gives you n minus 2 times n minus 3, CRn to the 4. 1 second. Minus 2 CRn minus 4 times n minus 1 minus 2 equals 0. This is all going to simplify down to n minus 2 times n minus 3 minus 2 times n minus 1 minus 2 times CR n minus 4 equals 0. And we can simplify that further to n minus 4 times n minus 2 times n minus 1 times n plus 1 times CR to the n minus 4 equals 0. And from this, we can find the values of n to be -1, 1, 2, and 4. Which is important because we're then going to be substituting these back into the FR equation as the powers of the R. So for the -1, we have that R is the -1 power. So forth, we get R is the 1, R squared for that term. Sorry, and CR to the 4th. And that is our new FR equation with the found n values. We know that C4 must equal to 0 because the equation does not contain an R4 term. The phi equation does not contain an R to the 4th term. We also know that C3 must be equal to the -1/2 V infinity because the R squared term in the psi equation has it's going to be equal to the FR sine. So our psi equation, when we substitute this in, is going to be equal to C1R to the -1 times C2R minus 1/2 V infinity R squared times sine squared theta. Wait, yeah, sine squared, right? Okay, yeah, VR is going to be equal to, we're now substituting in the C1, we're substituting in the FR equation into our VR and V theta. C2r to the negative 1/2 v infinity r squared sine squared theta 2 sine cosine theta. Here I'm just deriving the equation with respect to theta, which you would product rule it, but because sine squared theta is the only thing that is in respect to theta, the other things cancel out. So we're just going to get VR equals to V infinity minus 2C2 divided by R minus 2C1 over R cubed times cosine theta. All right, for V theta, we have 1 over R squared sine theta from before, and we're substituting in FR, or phi. We're substituting in the phi equation from above. C1R to the negative 1 plus C2R to the minus 1/2 V infinity R squared all times sine theta. And these are our equations for VR and for V theta in the equation. We're now going to use these two equations to find the C1 and C2 values, just simplifying the V theta equation. The sine squared is going to cancel out that sine. We're just going to be left with V theta is equal to V infinity plus C2 over R minus C1 over R cubed times sine theta. All of that is going to be over 1. Okay. So now we're going to be finding, using those two equations, you can get the C1 and C2 terms. C1 is going to be equal to negative 1/4 V infinity R cubed, and C2 is equal to 3/4 V infinity times R. Using these, we're going to plug these back in to the VR and V infinity equations to get them in terms of R and R, big R and little r. The VR equation is going to be equal to this times cosine theta, and V theta is going to be equal to negative V infinity times 1 minus 3/2 actually, times R over R minus 1/4 R over R cubed times sine theta. And these two equations are our velocity components. So the next step is going to be get to the pressure. The first thing we need to know is the R minus and theta components. We're going to use the Navier-Stokes equation to find the delta pressure over R and delta pressure over theta equation. So we have partial P over R is equal to 3 times mu V infinity over R squared times R over R cubed cosine theta. And we have partial P over partial theta times 3/2 mu R V infinity over R times R over R squared sine theta. These equations are going to be integrated on the boundary R to infinity, and the modified P, the delta P, is going to be going towards P0, or the initial P. So when this happens, we're going to be able to simplify this P equation here into P naught minus P GZ minus 3/2 of mu V infinity over R times R over R squared cosine theta. And this is going to be our pressure equation. Okay, so the final step is going to be finding the stress tensor components, tau, which are going to be obtained from the velocity distribution using the equations from B1. So we're going to be finding tau RR and tau R theta. So there's a couple of equations to find tau RR. Tau RR equals to negative tau theta theta and negative 2 tau phi phi. And we're going to be using the equation for tau phi phi because it doesn't involve any derivation. It's just negative u times 2 times 1 over r times 1 over sine theta times partial v phi over partial phi, which this is just going to be equal to 0 because we know from the equation D in the very beginning that phi has been set equal to 0 due to the steady state and because of the RE value. And the rest of this equation is just going to be the VR and V theta equations, which it's just going to be simple algebraic manipulation to solve this tau phi phi, which is equal to 2u over r times V infinity times 1 minus 3/2 r over r plus 1 over 2 r over r cubed cosine theta plus V infinity times negative 1. And I'm just pulling these again from the velocity functions that we got in part A. 1/4 r over r cubed. And this is going to be multiplied by cotangent, which is just cosine over sine, which the sines are going to cancel out. And we're now going to try to simplify this equation. So the first thing we know that we can pull out for this tau theta is going to be the V infinity and the cosine. Is we're going to pull out from the equation and we're going to simplify it down to just 1 minus 3/2 r over r plus 1/2 r over r cubed times, or no, just plus negative 1 plus 3/4 r over r plus 1/4 r over r cubed. We are going to be able to cancel out the 1 terms, and we can simplify the like terms further down into tau phi phi equals to negative 2 mu V infinity over r times negative 3/4 times r over r plus 3 over 4 r over r cubed. And the cosine term disappears because, yet again, we can't have theta in the equation, but the reason that cosine theta disappears is because the angular velocity for the tau phi phi is going to be equal to 0, and cosine theta at 0 is going to be equal to 1, so that got taken out of the equation, leaving us with just our simplified equation down here for tau phi phi. We do have to remember, though, what I've just done is because negative 2 tau phi phi is equal to tau RR, in order to get tau RR, we're going to be multiplying by this negative 2. And we're going to get this as our answer for the first tau RR stress tensor equation. For the next equation, we're going to be solving for tau r theta, which is equal to negative mu times r over partial r times v theta over r plus 1 over r partial theta over vr. Okay, so for tau r theta, we're just going to plug in the v theta equation for the partial r, and then we're going to plug in the vr for the partial theta, and we're going to be deriving. So I'm just plugging in the v theta equation from the velocities, and we have to derive this over r, which is going to be important. And then we are going to be adding 1 over r partial theta times v infinity. And this is just the VR equation from the velocities. 3/2 r over r plus 1/2 r over r cubed times cosine theta. And now we're just going to be doing the partials. So for the first one, we're going to be doing low d high d low. It looks complicated, but because we're taking a derivative with respect to r, and we know that sine theta cannot be with respect to r, it's just going to end up being r, because that was outside, times low, which is r, times the derivative of high, which we're going to product rule, but since the sine theta derived with respect to r is 0, we only have to do one side, which is going to be the derivative of this v theta equation times sine with a v infinity and an r on it, and then minus high d low, so we're just rewriting the v theta equation times the derivative of low, but since low is just r, the derivative is 1, and we're just writing the v theta equation. Make sure that negatives are always tracked, because lots of things are going to cancel out in this equation, and we want to make sure that they cancel out properly. And then over low is just going to be r squared. For the second half of the equation, we are deriving with respect to theta. So it's only going to be the cosine term up here, which when we derive is going to be negative sine theta, times the entire rest of the VR term. Let me write it down below. We have 1 minus 3/2 r over r plus 1/2 r over r cubed. And remember to watch the signs once again, because they are very important for canceling out in this equation. So now we're going to do some simplification. We notice that we can distribute this r back into the equation, which re-simplifies those r quarter terms to r3 and the r squared terms to r. We can take out a sine theta and a v infinity from every equation, and we also notice that each of these parts are going to be over an r because we cancel it out. So we're also going to take out a 1 over r from each equation. So it can be heavily simplified down, and we're just going to have that tau theta r is equal to negative mu v infinity. We took out a sine theta and a 1 over r, which just leaves us in the middle with the r over r terms. So we have negative 3/4 r over r minus 3/4 r over r cubed plus 1, because we distributed that negative to all these terms, minus 3/4 r over r minus 1/4 r over r cubed minus 1 plus 3/2 r over r minus 1/2 r over r cubed. And so first terms that are going to cancel out is just going to be this 1 and this negative 1. Can slash those. Second terms that are cancel out, we have the r over r terms to the first power are all going to cancel out with each other, which just leaves us with these r over r cubed terms, which we can simplify down to just negative mu over v infinity over r times negative 3/2 r over r cubed. Now we're going to do something. We're going to take out a 1 over r, and we're going to be plugging back in the 1 over r into the equation, which is going to raise the power of both the r on the top and the r on the bottom. First, we can simplify by taking out the 3 over 2. But now you see we're going to be putting the 1 over r from the equation back in, and we're taking out a 1 over big R, which is going to raise the power of the equation. So we have 3 mu v infinity sine theta over big R times big R over little r to the 4th power. And this is going to be our second stress tensor, tau r theta. The final thing we need to do is we need to take these two tau theta equations, and we're going to be finding our forces. The first force we have is going to be the normal force. So at every point on the surface of this sphere, we have force per unit area of negative P plus tau RR, where R is equal to big R. And for this force per unit area, we need to find the Z component of the force. And the Z component of the force is going to be equal to negative P plus tau RR, where R is equal to R, times cosine theta for the angle. We're going to multiply this by the surface element for the sphere, r squared sine theta d theta d phi, and we're going to get this integral, where r is equal to big R cosine theta r squared sine theta d phi, which we can assume that r, we're going to have that TRR is equal to 0, which simplifies it down to our new pressure equation, which we got by plugging in the tau RR at R is equal to big R to the integral. We're going to plug that, and we're going to integrate it to find our normal force function, Fn, is equal to 4/3 pi r cubed times pressure times gravity plus 2 pi mu r v infinity, which respectively are the buoyant forces and the drag forces caused by the form of the sphere. So these are two of the three forces that we're going to get on the equation. For the third one, we're going to need to substitute for the tangential force using the tau r theta equation. So for the tangential force, we're doing the same thing. We're solving for the z component of the force. We have tau r theta at r is equal to r multiplied by the surface element of the sphere r squared sine theta d phi, which is going to yield us the tangential force equation of the integral 0 to 2 pi, 0 to pi, times tau r theta, where little r is equal to big R, times sine theta r squared, sine theta d phi. We're going to plug in. We need to find out what our tau r theta equation from above equals when r equals to little r, which is easy because they only interact once in the equation, which is inside the parentheses. So this big R over little r, when they're equal to each other, is just going to be R over R, which equals 1. So we're going to cancel that out of the equation, which leaves us with this for our tau r theta equation. When we plug this back into the integral, we're going to find that the force transfer equals 4 pi mu times r v infinity over, and that is our final force. We're going to add this back to the other two forces to find the force total equals to 4/3 r cubed pressure times gravity plus 2 pi mu r v infinity plus 4 pi mu r v infinity. This is our final equation. We have the first term is our buoyant force found from tau rr. Second, also found from tau rr, is our form drag. And the final term is the friction drag we got from the tangential force. And that is everything we need.